This is lecture 13. So in the last lecture we discussed about uh, an architecture to bias an amplifier with while ensuring that there is input match, right? If I quickly draw the architecture, this is how it look like. So you have an antenna input, then you have a common gate configuration which provides the necessary input match, and probably you have a resistive load. This guy is biased with VDD, and we saw that directly connecting it is not a good option with respect to the input, so we had to AC couple with a capacitor. In order to bias this transistor, we had to provide a current supply, which was provided through a current mirror bias. The gate voltage of the main transistor M1 the gate voltage of the main transistor was obtained by a resistor divider, and we saw that it was necessary to put a large capacitor here, C2, to ground, while ensuring that C2 is much greater than the CGS capacitance in order to ensure uh, the current that is going into this transistor M1 actually comes out, right? Or rather, we have to ensure that the input impedance or the impedance looking in to the source of M1 was always uh, equal to 50 ohm, right? So that was something we had to ensure. So this was a V out. We also talked about what are the swing limits, right? We have to ensure that the voltage, each transistor had their own biases, right? While ensuring that the operating condition, or rather while ensuring that the input impedance and the operating conditions do not get disturbed, right? If you recall, we had, while doing so, we had taken the assumption that this voltage swings between, if the input is Vp sin omega t, right? So under matched condition, the voltage at the source of the transistor M1 goes from Vp by 2 to plus Vp by 2 to negative Vp by 2, right? So we had to ensure that the bias of the gate voltage of M1 is such that we have sufficient overdrive, while ensuring that this voltage never goes below 0, right, in the presence of signal swing. Okay, so now the question is that assumption still valid when we have this transistor M0 in place, right? When we have this transistor in place, clearly that assumption is not valid, because we'll have to ensure that this transistor M0 is also in saturation, right? So by the way, in all our analysis so far, we have neglected channel length modulation, right? So just to keep our hand calculation simple and to gain some intuition. Okay, so now the part that we did not consider in the previous lecture, but we have to now consider, is the fact that we have M naught, and this M naught has to be also in saturation, right? So M naught also must be in saturation to ensure that the bias current through M1 is not changing is not changing significantly, right? So essentially, to ensure the bias current through M1 does not change or rather remains constant. This statement is strictly valid if we neglect channel length modulation, right? But if we do not neglect channel length modulation, so let me also write it down. Strictly valid if channel length modulation is neglected. If we consider channel length modulation, then obviously there will be some changes in the current, but largely you will have constant current with some variation which probably is tolerable. Okay, so now the question is, what needs to be done to ensure M0 is in saturation? So clearly, so we said that this is I0 by n, this is 1 is to n. Right. So clearly we have to ensure that the drain voltage of M0 never goes one threshold voltage below the gate voltage of M0, right? So what is the gate voltage of M0? This voltage is nothing but S of M0 is equal to, is basically set by the VGS of M0A which is nothing but one threshold voltage plus 2 I naught over M by mu n C ox W by L n, right? So this guy cancels. So we essentially get one threshold voltage plus, this is an overdrive voltage, V overdrive voltage of M0. Okay, so if that is the case, then what is this source voltage supposed to be? Let me call this V1S. So therefore V1S must always be greater than 1 VGS minus threshold voltage of M0, which is essentially P overdrive of M0, right? So this is not only under quiescent condition, including signal swing, right? So which essentially means that I know, what do I know? Under matched condition, the signal swing is Vp by 2, right? So V1S minimum can be, so which means that V1S quiescent, so this is V1S minimum, right? So this sets the minimum. So what will be V1S quiescent? V1S quiescent must be greater than this V1S minimum plus that signal swing, and signal swing is Vp over 2, which means this has to be plus Vp over 2, right? So, and now if I want to bias just at this edge, then I know that my so this voltage becomes set, which means I have to ensure that the gate voltage of M1 is also fine, which essentially means that your Vg of M1 should be greater than V1S quiescent plus VGS of M1, which means this is equal to V1S. V1S quiescent is, what is V1S mean, plus Vp by 2, which means P overdrive of M0, right, plus Vp by 2 plus the VGS of M1, which is one threshold voltage of M1, plus the overdrive voltage of, right. So you have to ensure that your VG of M1 quiescent, VGQ of M1 is greater than equal to, this should be VGQ, right? I should not write VG because VG and VGQ are same, under, because the gate voltage is not changing at all. Okay. Okay. So this kind of gives you an idea how to bias the gate voltage. So we more or less have an idea now how to design a common gate amplifier, or rather a common gate input stage. I should not yet call it an amplifier, because we have not really talked about that amplification part other than at the right at the beginning of the lecture before last. But at least we understand that this contraption can give some amplification while ensuring that there is some amount of input match. Okay. So now there is one shortcoming that obviously you should be able to appreciate in this architecture is the is the voltage that you require just to ensure that things are biased properly, right? Your transistors are biased properly. For example, if I take a overdrive voltage of, let's say, 200 millivolt, right? So then this is about 2.2 volt. Threshold voltage typically can range anywhere between 300 millivolt to 500 millivolt. Let's take 400 millivolt. This is 0.4 volt. This threshold voltage, let's say, is 0.2 volt. And if you want to accommodate, let's say, a 0 dBm input signal, now if you calculate the 0 dBm input signal, which essentially means that it has like 300 millivolt of amplitude, right? So effectively you about 314 315 millivolt of amplitude, which essentially means that Vp by 2 is of that order, right? So which essentially means that you get about 300 millivolt here. So you see the VGQ becomes how much? 0.2 plus 0.3 is 0.5. This VGQ itself becomes 1.1 volt, right? And this is assuming that there is absolutely no margin anywhere. Okay. Similarly, if I have to think about how much should your VDD be, so what is the requirement on VDD? The VDD has to be, right? VDD has to take care of the drop across the resistance, then it has to take care of the drop across M1, and then this drop has to be, while the source voltage has to be above the minimum required voltage value, right? So as you can see that quickly, the stacking of these transistors can become infeasible, especially if you are working with voltage supplies which are like 1 volt or less than 1 volt. So moment you go to lower voltage supplies, and stacking of transistors becomes a big problem. So what's the solution? The good thing about designing circuits for RF is we can use an element which we normally tend not to use in analog circuits, and that element is an inductor. And why is it a good thing? The good thing is because the impedance of an inductor goes up with frequency, right? So we can then start using inductors to essentially give us to mimic an open circuit if the value of the inductor and the frequency of interest is of certain value, right? So is above certain value. Okay. So what I'm essentially saying is an inductor, its impedance ZL, which is we all know is j omega L. So mod ZL for, let's say, mod ZL equal to omega L, which is 2 pi times frequency times L. So for L equal to 1 nanohenry, right, at f equal to 1 gigahertz, you are getting an impedance of about 6 ohms. Okay, so now if you this might not seem much, but let's say I use L to be equal to 10 nanohenry, then this goes to 60 ohms. And let's say I am interested in not at 1 gigahertz, I am interested in uh, 2, 3, 4 gigahertz, then obviously the impedance associated with it can quickly go to like more than 100 ohm, more than 200 ohm, and close to 500 ohm, and so on, right? So since ZL increases with omega, we can use it if necessary to mimic a load. But why would you like to at all use ZL to mimic a load? We would like to use it because it does not have any Poisson drop, right? So good thing is, so big positive is no Poisson voltage drop. Another big positive is sufficiently large value of L can mimic, or I should simply say sufficiently large L can mimic a current source. Why? Why can we say that? It's because what is the property of a current source? Property of a current source is, number one is obviously it should not be able to, you should not be able to change current, and number two, you should get the impedance across the current source should be infinite. Now if the value of L is infinite, then obviously the impedance is infinite, and we know that inductor resists any change in current. So if you have some current inside the inductor, initial current, it will be able to hold on to it will be able to supply the current for infinite time. But I mean, that is something ideal scenario. We all know that's never the case. uh, but as you can see that as frequency increases, right, since the impedance of the inductor also keeps on increasing, there is a likelihood that we should be able to approach a decent current source. Just like a capacitor, a sufficiently large capacitor can act as a battery, because a capacitor is a storage of voltage, and a sufficiently large capacitor, right, does not allow its voltage to change, and it also gives you short circuit impedance to its signals of certain frequency and above. Similarly, a sufficiently large inductor uh, can resist any change in current and provide an open circuit impedance to certain signals of certain frequency and above, right? But the key thing is an inductor does not have any quiescent voltage drop, right? So which essentially means that if I go back to our original circuit, I need not have this. I need not bother with that voltage drop across the load resistance, right? If I can replace that R with an inductor, right? So let's try that. So I'll not draw the entire circuit. I will just replace. I'll draw the initial circuit, initial part of the circuit, and let's assume that this guy is voltage biased. This guy is also biased. accurately, and this is VDD, right? So instead of the revision 2 is we do not change anything, we just replace that R with an inductor. So in the circuit in the left, the VDD has to be, so if this is I naught, the VDD had to be, so this voltage Vs min was necessary. You must needed at least one overdrive uh, uh, voltage across the VDS of this transistor, right? And you would have required an additional drop of I naught times RL. So this is RL, right? So VDD had to be greater than Vs min plus V overdrive plus I naught RL, correct? So now what's the scenario? So now the scenario is this voltage is still staying at Vs min. This overdrive I still require, but the quiescent voltage drop across the inductor is 0, which means that my VDD has to be greater than only Vs min plus V overdrive, right? And what was Vs min plus V overdrive? Vs min, where were we? V1s min, right? So V1s min was like 0.5 volt, right? And V overdrive is 0.2 volt. So as long as VDD in principle, right, is greater than 0.7 volt, it should work, right? But on the circuit on the left, you need to have a on top of 0.7 volt, you need to have a budget for I naught RL. Now, if you want to have large gain, that is, you want to increase RL, then obviously you need to budget for that extra voltage drop across the resistance, right? So this is nothing new to any RF amplifier. This is true for any common source amplifier, any analog amplifiers that we have studied in the past in our earlier courses as well, right? So what else can we do? Now just because I 5 minutes back I also said that an inductor can probably mimic a current source. A sufficiently large inductor can mimic a current source, right? Okay, before we proceed, let me do one thing. So let's take some example values to understand what will be the value of the inductor that we just replaced, right? So we understand that there is a input current under incremental condition, right? Under incremental condition, you have this input current that flows in, which is Vp by 2R, or I write it in the form of I, Vi by 2R, and this current eventually flows into the resistance RL, and it provides a voltage of, incrementally, your voltage is, this is V naught, or incremental V naught, that is small V naught, is Vi by 2R times RL, right? So your gain essentially is RL over R, right? And so I will just simply write it as Vi by 2 times RL over R. And we know that R is 50 ohm, right? Or if RL, if you are looking for a gain of let's say 5, then RL has to be like 250 ohms, right? In the circuit on the left, you still have the same thing. You have this current, that is Vi by 2R, but now the voltage that you are accruing over here, that is V naught is Vi by 2R times the impedance that you are seeing for the on the inductor, that is j omega L, which means that mod of V naught by Vi by 2 is essentially omega L by R. If you know your omega, which in RF applications almost is true, because you do not want to, you know at which frequency range you are transmitting or receiving, so omega is kind of known, right? So let's say if omega is 2 gigahertz, rather f is 2 gigahertz, then in order to get omega L, so at f equal to 2 gigahertz, so in order to get RL to be equal to, or omega L to be equal to 250, you want L to be equal to 250 by 2 pi, that is 6 times 2, 12. So this is how much? 20 nanometer approximately. I should write approximate. These are never equal. So like very crude approximations, right? So be mindful of the fact that a 20 nanohenry inductor is not a small inductor. It can take significant amount of chip area, uh, and 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 a lot of effort needs to be done in order to ensure that we get good inductors of these values. There will be a separate lecture later on where we talk about passives, where we'll briefly touch upon how to go about designing inductors. Okay, but for the time being, uh, just to get the course moving forward, you should keep in mind that capacitors of the values of hundreds of picofarad and inductors of the value of tens of nanohenry are, and they take significant amount of chip area. We do not use them unless they are absolutely necessary. Okay, so in this case, we are like, you see that L of 20 nanohenry is probably borderline. We are getting to borderline scenario where we probably do not want to get beyond, much beyond that. But uh, But the good thing is that if you think that we can get away with a lesser gain, then you can obviously reduce the value of L. Or if you are trying to go to higher frequency, also you can reduce the value of L, which is not the case if you use a resistor where the quiescent value of quiescent drop of the resistor dictates the amount of power supply that you will always require. Okay, okay. So by the way, I also have to put a caveat. So this analysis that I did here, right? So this is not including the, the drop that is required for the incremental current, right? So without even considering incremental current, right? Without considering incremental. Okay. So similarly, we can also get rid of the bottom transistor, that is this transistor M0, right? If we choose to use an inductor which has a sufficiently large value so that it behaves like a current source. Now, when I say it behaves like a current source, or it behaves like a large impedance, what do I mean? I essentially mean this. So you have, what is the effective impedance? These are all incremental. So what is the effective impedance looking into this node? So effective impedance looking into this node is looking up under matched condition, this is 50 ohm. Under matched condition, this is also 50 ohm. So effective impedance Rn is 25 ohms, right? So all you have to ensure is, if we are putting a current source here, right? So the impedance of the current source associated with the current source, with the non-ideal current source, has to be much larger than 25 ohms. Then we are done, right? So all you have to ensure is, if we put an inductor here at a frequency omega where it gives an impedance of j omega L, all we have to ensure is that at omega L, or omega L has to be much greater than 25 ohms. So if then the inductor, we call it LS, connected to the source, as a current source. So in effect, the current that comes out from from this source goes here and nothing goes here, right? So nothing goes here. So if that's the case, then we do not have a problem in that. Okay, but uh, if you are paying attention, you would now point to me and say that, hey, what about the DC value across the inductor? So clearly the DC value across the inductor is 0, which means that what about the effect of body bias for the transistor? So here this is quiescent is 0, right? So your when the signal swings, here the signal swing will go from 0, go up and go down. It can go to minus Vp by 2. Now in one of the earlier lectures I had pointed out that this can be problematic because of you have the body of an NMOS which is connected to ground, right? And you have essentially this parasitic diode which is inbuilt, and if the source voltage now goes below one threshold voltage, or rather the cut-in voltage of the diode, then we have a problem, right? So that is why if you have to use this type of topology, you have to ensure that you connect the uh, body to the source all the time. This becomes your input. Okay. Okay, but the issue is not all technologies will allow you to do this. Why? Why is this a technology issue? This is technology issue because what is the cross section of an NMOS transistor? So again, this is the uh, gate oxide, and you have, let's say, the right side is the source, then plus P minus, and you have a body connection with P plus. Okay. So now, when you are saying that I am connecting this is the source and this is the body. When you are saying you are shorting the source and the body, what are you essentially saying? You are essentially saying that I am shorting this N and the P, right? So how can you short this N and the P, right? When the source is not grounded, particularly because this P is shared across all NMOS transistors in your chip. So this is a shared P substrate, which means if there is another transistor, another NMOS transistor totally unrelated to this, whose body you want to ground, then you will not be able to ground because these two are connected, right? So that is why when I said that you have to first check with your technology, with your PDK provider, that whether this is allowed. In certain technologies, it is allowed to have a separate well for your NMOS. What I mean is that in some technologies, it is allowed to have a N-well implant. Call this N-well implant, and on top and inside this N-well implant, we make a mistake here. There is an N-well implant. Inside that N-well implant, we make another P implant. Let's call this P minus. and inside this P minus we create a P plus stub and we call this the body. Now this body and this source can short, right? So in certain technologies this is called a deep N well implant. So in certain technologies these deep N wells are available. If they are available, then you can short the body and the source, and you can do this. Okay, but there are certain issues with this particular. Even if it is available, we'll talk about that sometime later. Okay, so now a quick recap of what we studied so far, at least from the perspective of receiving a signal. So we saw a few topologies. Like if I go back 2 or 3 lectures, we saw a few topologies which are helpful in ensuring that there is a matching, right? Among them, we took one topology, namely the common gate amplifier or the common gate topology, and we tried to see how we can use it not only to get matching but also maybe to get slight amount of signal amplification. Then we saw an issue with with the parasitic capacitance, the CGS of the transistor M1. We saw an issue with this capacitance, and we were able to resolve it by putting a large capacitance C2 to ground. Then we saw some issues with biasing with regards to if the power supply available to us is like is comparable to the threshold voltages and it's not like 3 volt or 4 volts. Then we kind of try to fix those issues by putting in inductors. Granted, the value of the inductors that we require might sometimes become prohibitively large, and because of that, what generally people tend to do is, if at all that is required, you can put an off-chip inductor, right? So you can put a large off-chip inductor and do not burden the chip with large on-chip inductors, which can take up a lot of area, and that is actually done. Okay, so what we'll do next is to slightly dive a bit more into the details of details on what are the limits of these type of architectures with regards to frequency of operation, right? So there are several limits that you will see later on, which will come to the fore as we discuss more and more uh, um, higher order effects. But for the next part of this lecture, what I would like to focus on is to understand um, what are the frequency limits uh, that can limit the performance of our uh, of a network, right? And what we can do in order to alleviate. Okay. So let's take this common gate configuration as our vehicle of choice, and let's move forward with that, right? So what I'll do, I will not draw the entire circuit from now on. I'll only draw the common gate part, and I will assume that things are connected next to each other and we understand how it works. Okay, so let's do that. So we have this common gate topology. In the incremental sense, this is supposed to be grounded, right? You put a large capacitor and you ground that. A current is supposed to be coming in from here. The current is supposed to be Vp by R, Vp by 2R if it's matched, and so on. And we expect this I in current to go out into a load, and the short circuit current that is supposed to be there. So this is a load. If it's a resistive load or inductive load, it's a load, right? And we understand there is this CGS capacitor associated with every transistor. Okay, so let's try to figure out what is the short circuit current that comes out of it, right? So let's say, in order to find out short circuit current, what do I need to do? Incrementally I short it. If I close the circuit, so this is what it should look like. So I have a, let's say, I in, and this is a short circuit. I'm interested in finding out what is I out. So what will be I out? So clearly this I in goes here. What is the impedance looking up? If I neglect channel length modulation, looking up, impedance is 1 over Gm. right? What is the impedance looking this side? This is 1 over CGS, 1 over omega CGS, 1 over j omega CGS. So essentially, what is the current? I out is essentially, is a ratio of conductances, right? So I out is essentially I in times Gm by Gm plus j omega CGS, which essentially means that if I write it in terms of I out over I in, which is 1 by 1 plus j omega CGS by Gm. What is this telling us? This is essentially telling us that at low frequencies, right? So when omega is much less than Gm over CGS, right? I out is equal to I in, right? And as frequency increases, I out becomes lesser and lesser as compared to I in, right? So when omega is much greater than Gm over CGS, I out is essentially equal to, let me call the mod of I out is essentially equal to I in times Gm by omega CGS, which is much less than I in. Okay, so now what are you seeing? What we are seeing is as frequency increases, this CGS capacitor, which is by the way a part of the transistor, is stealing away current, right? And larger the amount and the amount of the current that gets stolen is higher at higher frequency than at lower frequency, right? So which essentially means that the amount of current that is available at the output, right? So I out ultimately has to flow into a load and create a voltage. If I out itself is small, that is the short circuit current itself is small, you are not going to get enough voltage at the output, right? So which means that there seems to be a fundamental limit, right, with respect to the amount, with respect to the frequency at which this particular configuration can operate at. Okay. Now you will see that this expression of Gm by CGS is a very common terminology that will keep coming, and it will keep coming in discussions of frequency of operation whenever you have a MOSFET associated in the discussion. And this thing, that Gm over CGS, is as a name. We call it omega t or 2 pi ft, where ft is the transit frequency. Right? The nomenclature comes from BJT days. It's basically how it is representation of how fast the charges move from one end to the other. Faster it moves, higher the ft. For the purpose of this discussion, all we need to understand is that if both Gm and CGS are properties of transistors and they are tied together, then Ft is probably also a property of a transistor in a particular technology. If that is the case, then looks like there is a limit beyond which this particular topology is not going to work, because the parasitic capacitance is going to short out my current and nothing is going to come out. Okay, so before we proceed, what I would like to show you this effect of Ft and how it in certain other different configurations which you might be more familiar with, and hopefully you will also get some intuition as to why this is of some interest. So let's say I have a common source amplifier, right? So let's say I have a common source amplifier, and I am only drawing the incremental part, right? So which means that the drain is open, this is Vi, and let's say one common source amplifier is driving another common source amplifier, okay, of identical size, which can happen if you want to get higher gain. Let's say one common source amplifier is giving you a gain of 4, you want a gain of 16, you put the same thing one next to each other, If one is giving you 4, two of them cascaded will give you 16, and so on, right? So that's the whole idea. So in a very simplistic model, if I assume that this CGS here and this CGS, if they are identical, these two MOSFETs M1 and M2 are identical, then CGS capacitances are also identical, right? And there is some load connected to it, so we don't have to bother about the load right now at the output of M2. So, what is the incremental current that is flowing out of M1? And I am interested in finding out V0 with respect to V1. So, the incremental current that is flowing out is Gm times Vi. So, what will be V0? So, V0 will be this incremental current going into the capacitor, and this capacitor is essentially CGS, which is the output, what is the input input capacitance of M2. Note that I am neglecting any other capacitance, like this is a gross oversimplification. So if I neglect that, then V0 is essentially Gm times Vi by j omega CGS, and which means that your mod of V0 over Vi is Gm by omega CGS. And if I again define Gm by CGS as omega t, this is omega t by omega, right? So what is this basically telling you? This is basically telling you that if you wish to get a gain out of your common source amplifier configuration in its very simplistic format also, you are going to get a gain till a frequency of omega t, right? So V0 over Vi is greater than 1 if omega is less than omega t. If your frequency of operation is beyond omega t, then you are not going to get any gain, right? Similarly, there is another popular way of giving an intuition about the importance of omega t, and that is this. So let's say again you have a transistor which is as in biased in saturation, and we are showing only incremental model. Let's say I am driving this transistor with a current source, right? So I in, which is incremental. This is not a bias current, okay? And I am interested in the current that is coming out, okay? So again there is a capacitance here CGS. I am interested in the current that is coming out. So what will the voltage that is going to develop? This voltage at the voltage that is developing across the VGS. Your VGS is essentially I in by j omega CGS, right? So I out is basically Gm times I in, Gm times VGS, which is I in times Gm by omega CGS, which means mod of I out by I in. That is the current gain, that is potential current gain that you can get, is essentially again omega t over omega. So this is greater than 1 if the operating frequency is less than omega t. Okay, so so as you can see that this omega t is not particular to that common gate configuration, right? Depending upon whether you are using a common source amplifier, whether you are trying to get a current gain out of your MOSFET, you always see that you are kind of limited by this factor, by this weird frequency omega t, which is the ratio of the transconductance that you are getting, right, in the MOSFET divided by the gate to source capacitance of the MOSFET. Sometimes you are going to see that in some definitions, actually, if you have to be more accurate, you'll have to take into account this capacitance also, right? This is, if I call this CGD, then you are going to see that the effect of this current gain that you are going to see will also have the CGD taken into account. But I mean, for the purpose of this discussion, we'll neglect the effect of CGD. One of the other reasons is that generally CGS is often much larger than CGD if the transistor is biased in saturation, and we can for the purpose of this discussion, we can safely safely neglect that. And if at all we include CGD, the value of omega t will will actually come down and it will not go high up. Okay, so so now, which essentially means that we'll have to, the next step should be to try and understand what we need to do to ensure that this omega t, which seems to be a very important factor in the operation of a transistor, is as high as possible, right? So we'll stop here, and that will be the starting point for the next lecture.